Design and analysis of a bus terminal building. Abstract. The design and analysis of bus terminal building is carried out. The manual designing of buildings include the design of foundation, design of column, beam, slab, stair etc. using a set of procedures and building codes such as IS 456. Here the structural analysis using STAAD Pro V8i SS6 is carried out. Keywords: deflection, bending moment, shear force, assembly building. Introduction. In all spheres of human life, buildings are always necessary to satisfy human need. This study mainly focuses on the analysis of an assembly building i.e. municipal bus terminal. Pandalam using STAAD Pro V8i SS6 and manual designing. In this study each structural part is analyzed. The bending moment, deflection, shear force etc. are analyzed. 2. Objectives. Generate structural framework. Creating model using STAAD Pro V8i. Carry out the structural analysis and manual design, thus ensure the structural stability. 3. Building informations. The proposed bus terminal is a 2-story building. It consists of shops, office, staff room, toilet complex etc. There are 2 openings provided for the entry and exit of buses. 4. Specifying loads. These are self-weights of the structure to be designed. The dimensions of the cross-section are to be assumed initially, which enable to estimate the dead load from the known unit weights of the structure. The values of the unit weights of the materials are specified in IS 875:1987, Part I. Dead load includes self-weight of columns, beams, slabs, brick walls, floor finish etc. The self-weight of the columns and beams were taken automatically by the software. The dead loads on the building are as follows. Here instead the load given to the structure are dead load, self-weight and UDL due to brick of 18.6 kN/m, live load of -3 kN/m2 and load combinations. V. Manual design and STAAD analysis. A. Design of pile cap. Data is: number of piles equals 4. Pile diameter equals 500 mm. Spacing of piles 2 HP equals 2 x 400 equals 800 m. Concrete mix equals M20. Steel grade equals Fe 415. Length of pile equals 23 m. Soil type is weak clayey soil. Assume unconfined compressive strength as 0.058 N/mm2. I.EUCS equals 58 kN/mm2 Cu equals 582 equals 29 kN/m2. Assume equals 0.9, therefore ultimate capacity of a single pile CU equals CUNCAP plus quas equals 965.726 knots. Spacing of pile equals 2 HP equals 2 times 500 equals 1000 mm. Dimension of column B times D equals 0.45 times 0.45 m. Factored load equals 1704.6 kN. Factored moment equals 101.085 kN. Safe pile load capacity equals 965.7 kN. 1. Pile cap dimension. Length and breadth of pile cap equals 1000 plus 2 times 250 plus 150 times 2 equals 1.8 m. Depth of pile cap equals 2 HP equals 1000 mm equals 1 m. 2. Check for pile load capacity. Self-weight of pile cap equals 1.8 times 1.8 times 1 times 25 times 1.5 equals 121.5. Factored load from column, Pu equals 1704.6 kN. Total factored load equals 121.5 plus 1704.6 equals 1826 kN. No if pile equals 4. Y ordinate of pile cap equals 0.5 m. Mx equals 101.08 and compressive load in pile about x-axis equals pun plus mxyy2 equals 953.38 kN. Design working load equals 953.382 equals 635.58 kN 965.7, hence safe. 3. Bending moment. mu equals 953.38, 1 to 0.45, 2 equals 262.18 kNm. 4. Check for effective depth. Mu equals 0.138 dfck d2 equals 262.2 kNm d2 equals 262.2 times 1060.13 times 25 times 450. D equals 410 mm required provided hence checked. 5. Check for punching shear. Punching shear at a distance d/2 from face-off column equals 1704.6 kN. Perimeter of critical section equals 2, 1800 plus 922, equals 5444 mm. Punching shear equals 1704.6 times 1035444 times 922 equals 0.399 n/mm2. Allowable shear stress for M25 equals 0.25 VFCK equals 1.25 n/mm2 0.339/mm2. Hence safe. 6. Main reinforcement. Mu equals 262.2 kNm K equals mub2 equals 0.17135 AST min equals 0.12100 times 1800 times 922 equals 1991.52 mm2. No of bars equals 1991.52201.1 equals 9.90510 bars. Therefore provide 16 mm, 10 bars at bottom. Reinforcement at top. Minimum AST equals 1991.52 mm2. Therefore provide 16 mm, 10 bars at top. 7. Check for one-way shear. Maximum shear force at facing of column equals 958.38 kN. Shear stress equals 0.577 n/mm2. For PT equals 0.2% TC from is 456 equals 0.33 n/mm2. Shear to be carried by stirrups, VU equals 0.577 to 0.33, times 1800 times 922 times 10-3 equals 409.92 Vud equals 4.446 kN/m. Provide 10 mm, 4-legged stirrups at 120 mm C/C spacing. Coorct _recover_recover_recover model _page 0001.jpg. Fig 8 pile cap detailing. B. Design of column. Column number 380. Grade of concrete equals M30. Grade of steel equals Fe415. Characteristic compressive strength of concrete. FCK, n/mm2, equals 30. Characteristic yield strength of steel. Phi, n/mm2, equals 415. Unit weight of concrete, C, Kn/m3, equals 25. Partial safety factor for concrete equals 1.5. Exposure condition equals mild. Nominal cover to exposure condition, mm, equals 40. Assumed effective cover all around, d, mm, equals 40. 1. Dimensions of the column. Breadth of the column b, mm, equals 450. Depth of the column d, mm, equals 450. Least lateral dimension equals 450 mm. 2. Design factors. Factored load, Pu equals 2208 kN. Factored moment acting parallel to the larger dimension, Mux equals 36 kNm. Factored moment acting parallel to the shorter dimension, Mu equals 48 kNm. Assume percentage of steel equals 1.5%. 3. Moment in XX direction. dd equals 40450 equals 0.090.1 puff d equals 2208 times 100025 times 450 times 450 equals 0.436 0.44 pfck equals 1.525 equals 0.06 muff d2 equals 0.07 mux equals 0.07 times 25 times 450 times 4502 equals 159.46 times 106 nmm. 4. Moment in y direction. 5. Calculation of PUs. 1.5% of steel is sufficient. 6. Calculation of reinforcement. P equals 1.5% 100 ASTBD equals 1.5 AST equals 1.5 times 450 times 450100 equals 37.5 mm2. Assume 16 mm bars. Know of bars equals ASTA equals 15.1116 bars. Provide 16 billion Argentine pesos of 16 mm diameter. The STAAD diagrams are the following. Spapture.png. Fig. 10 dimensional details of member 380 in the structure. Caftour.png. Fig. 11 reinforcement details of member 380 in the structure. Cafrpture.png. Fig. 12 shear bending diagram of member 380 in the structure. Delton380e.png. Fig. 13 deflection diagram of member 380 in the structure. C.design of beam. Beam.png. Fig. 14 beam number 4 in the structure. Beam number 4. Clear span equals 4.2 m. Live load equals 12 kN/m. FCK equals 25 N/mm2. Phi equals 415 N/mm2. SUD equals 7001100 plus 0.87 Phi equals 0.48. Assumptions of cross-sectional dimensions LD equals 15.4200015 equals D. D equals 280 mm 300 mm. D equals D plus 50 equals 350 mm dB equals 2. B equals 175 mm 200 mm. 2. Load calculation. Self-weight equals B times D times .con equals 1.75 N/mm. Dead load equals 1.75 N/mm. Design load equals DL plus LL. .con equals 20.63 N/mm. 3. Design bending moment. BM equals WL28 equals 52.22 kNm. 4. Calculation of limiting value of moment. Mu, lim equals 0.36 SUD 1-0.42 SUD FCKBD2. Equals 62.08 kNm. BM, mu, lim. Therefore under reinforced. 5. Reinforcement calculation. Mu equals 0.87 Phiest 1 Phiest. AST equals 572.60 mm2. Assume 16 mm bars. Know of bars equals total area of 1 bar equals 2.844 bars. 6. Design for shear. VU equals OL2 equals 46417.5 N/mm2 TV equals VOBD equals 0.77 N/mm2. 7. Design shear strength. Percentage of steel equals 100 ist equals 1.0048 TC equals 0.64 N/mm2 TC max equals 3.1 N/mm2. 4.png. Fig. 15 dimensional details of member 4 in the structure. Beam.png. Fig. 16 reinforcement details of member 4 in the structure. S4.png. Fig. 17 shear bending diagram of member 4 in the structure. D4.png. Fig. 18 deflection diagram of member 4 in the structure. D.design of slab. Fig. 19 slab 707 in the structure. Slab number 707. Size 4.2 times 2.4 m. M25 and FE415 are used. 1. Type of slab. LYLX equals 4.22.4 equals 1.75. Therefore it is a two-way slab. 2. Depth of slab. LD equals 20 D equals 420020 times 1.5 equals 136.66150 mm. Effective span equals clear span plus D. Equals 4200 plus 150. Equals 4350 mm. Depth D equals 150 plus 20 equals 170 mm. 3. Design load. Design load equals 1.5, DL plus LL. equals 1.5, 4.25 plus 3 equals 10.875 kNm2/4 m along x and y. He slab is restrained. From is 456, equals 1.75. Equals 0.1. Equals 0.056 mx equals .xwlx2. Equals 0.1 times 10.875 times 4.3502. Equals 20.577 kNm equals .ywly2. Equals 0.056 times 10.875 times 4.352. Equals 11.523 kNm. Shear force equals WL2. Equals 10.875 times 4.352. Equals 23.65 kN. 5. Check for depth. D equals Vmx 0.138 FCKB equals V 20.577 times 1060.138 times 25 times 1000 equals 77.229 mm. Hence, D required provided. 6. Calculation of AST, short san. Mu, lim equals 0.87 Fiest, 1est fib times FCK. AST equals 397.27 mm2. Assume 10 mm dia bars. S equals 1000 ost. Equals 197 mm. 195 mm. Provide 10 mm dia bars at 195 mm C/C along shorter span. 7. Calculation of AST, long san. D equals effective depth, 0.5 dia of my bar plus 0.5 dia of main bar. Equals 140 mm. Mu, lim equals 0.87 Fiest, 1est fib times FCK, AST equals 234.422 mm2. S equals 1000 ost. Equals 334.994 mm. 330 mm. Provide 10 mm dia bars at 330 mm C/C. 8. Check for deflection. LD, min equals LD, basic times KT times KF times KS. Equals 20 times 1.7. Equals 34, LD, max equals 4350150. Equals 2934. Therefore the slab is safe. 9. Check for shear. VU equals WL2 equals 23.65 KN2 equals VUBT equals 23.65 times 1031000 times 150. Equals 0.157. Percentage of steel equals 100est equals 0.264. Design of stairs. Screenshot _20003233-195922.jpg. Fig.20 Staircase details. Material constants. Concrete, FCK equals 25N/mm2. Steel, Fy equals 415N/mm2. 1. Dimensioning. Height of each flight equals 4.352 equals 2.175 m. Let the tread of steps be 300 mm. Rise of stair equals 0.145 m. Width of stair equals 1.9 m. Effective span, LE equals 8.4 m. Let the thickness of waste slab be 150 mm. Use 12 mm. Bars. Assume, clear cover equals 25 mm. Effective depth equals 119 mm. 2. Loads on landing slab. Self-weight of slab equals 0.15 times 25 equals 3.75 kN/m2. Finishes equals 1.25 kN/m2. Live load on slab equals 4 kN/m2. Total equals 9 kN/m2. Factored load equals 1.5 times 9 equals 13.50 kN/m2. 3. Loads on waste slab. Dead load of waste slab equals thickness of waste slab times 25 times VR2 plus T2T. equals 0.15 times 25 times V 0.1452 plus 0.320.3 equals 4.165 kN/m2. Self weight of step equals 0.5 times R times 25 equals 1.8125 kN/m2. Floor finish equals 1.25 kN/m2. As per is 875, Part 2, 1987, Table 1. Live load equals 4 kN/m2. Total service load equals 11.228 kN/m2. Consider 1 m width of waste slab. Total service load /m run equals 11.228 times 1 equals 11.228 kN/m. Factored load W equals 1.5 times 11.228 equals 16.842 kN/m. As per the UDL of the landing slab and waste slab. Reaction RA equals 45.414 kN. Reaction RB equals 49.626 knots. 4. Bending moment. To get maximum bending moment, take shear force at x distance from support B equals 0. Thus obtained x is 2.95 m. Maximum moment at x equals 2.95 m. Mu equals 73.1187 kNm. 5. Reinforcement calculations. MUB2 equals 5.16 N/mm2. Percentage of steel, PT equals 1.19%. From SP16, Table 3, therefore AST equals PTBD 100 equals 1416.1 mm2. Minimum steel equals 0.12% cross-sectional area. Equals 142.8 mm2. Use 12 mm bars, spacing equals 1000 ost equals 79.82 mm. Provide 12 mm bars at 80 mm C/C. Maximum spacing equals 3D equals 3 times 119. Equals 357 mm or 300 mm, less. Hence, provide reinforcement of 12 mm bars at 80 mm C/C. Distribution steel equals 0.12% cross-sectional area equals 142.8 mm2. Provide 8 mm bars. Spacing equals 1000 ost equals 351.82 mm. Maximum spacing equals 4D equals 476 mm. Hence, provide 8 mm diameter bars at 350 mm C/C. 6. Check for shear. As per is 456:2000, Clause 40. Maximum shear force, V equals 49.626 knots. Nominal shear stress TV equals VUBD equals 0.417 N/mm2. Max value of shear stress. Max equals 3.1 N/mm2. To get design shear strength of concrete, 100 ASIB2 equals 0.090.15. From is 456, 2000, Table 19. TC equals 0.64 N/mm2, TC max. So, shear reinforcement is not required. 6. 3D model of bus terminal. The 3D model of the bus terminal building is prepared. The model is prepared as per the plan and other details. IMG 20203211042222.jpg. Fig.21 Elevation of model. IMG _200324_154407.jpg. Fig 22 Model of bus terminal. 7. Conclusion. The structure is completely analyzed using STAAD Pro V8i. The structural components of the building are say fine shear and flexure. Amount of steel provided for the structure is economic. Proposed sizes of the elements can be used in the structure.